Woohoo! Welcome back. Tonight we're working with transformations of functions. And for this last video, we're going to be talking about reflections and possibly the prettiest graph that I've created for this chapter, this section. So let's go ahead and get started. The graph is a little bit of a lot, so let's dig in and see if we can make it make sense. It's just very pretty, I think. So we've got 4 graphs here, and I know it's hard to see, but basically I've mixed some metaphors. So I've got the absolute value of x, and I also have the opposite of the absolute value of x. Then, just to make things exciting, I've got x cubed, and then, and then I don't have h again, I have k. Woohoo. K of x, which is the opposite of x cubed. So as we're looking at the actual functions here, we can see that g of x is just f of x with a minus applied on the outside. And then k of x is just h of x with a minus applied on the inside. And so we're going to take a look at the difference between these two because I think they're very cool. And then we're going to need to review what is what on this graph. So let me remind you, this red graph that looks like a V, that one is actually the absolute value of x. So this is f of x, which is the absolute value of x. And the reason it makes sense is because when x is positive, y is just whatever x is. And when x is negative, y kind of, instead of going straight down, it bounces back because the absolute value keeps the whole thing positive. So that's why we have that weird little corner there. The corners are very unusual in graphs. They are, it turns out, they're going to be very difficult when it comes to calculus. So unfortunately, we're generally going to have to steer clear. But for right now, we can play with absolute value a little bit because it won't hurt anything. So that is our f of x. Now, h of x is a power of x, and the powers are generally going to be very smooth. They're not going to have little corners anywhere. They're going to be curves, like a parabola. So it turns out that this graph right here, and you can see the top part of it actually does look a little bit like a part of a parabola. And I'm realizing I left off the arrows. Let me write those in. There we go. The right part does look like a piece of a parabola, but interestingly enough, it extends down below. And that's x cubed. And let's think about what x cubed does. X cubed is kind of almost the opposite, not exactly the opposite, of what's going on with absolute value. When we've got absolute value, it says, don't care what x is, the output will always be positive. And with x cubed, we're saying, remember with the odd exponents, if you put a negative in, like if we had -1, the quantity cubed, we would get -1. So x cubed preserves sign. So when x is positive over here, y is positive. Over here, when x is negative, y is negative. So we've got these two different kind of philosophies. One is that sign matters, and one is that doesn't care. Don't care about the sign. Now let's look at our transformations. So you can kind of from this figure out, I know there's a little gnat here that wants to learn about transformations. That's awesome. So hopefully you can see that there seems to be, and it's interesting because I said the word reflection, and it looks like there's like a mirror image, like it's the reflection in a, like in a body of water or something right here. And this is g of x. And let's talk about why that makes sense. Why does it make sense that you just take the red one and flip it upside down? And the answer is because we're taking the absolute value of x, which will turn out to be positive or 0, and then we're going to apply a minus to it, which is going to take every positive answer and give us a negative answer. So, for example, here's a point right here. The point 22 reflects down here, and we get the point 2, negative 2. So the y value reflects. And we imagine that the x-axis is like the water. So it's the mirror image. It's this image in the water. So this is g of x, which is the opposite of absolute value of x. And you can see that for every point up here, there's another point down here. So it's reflected. And that's what we're imagining. In this case, y is going from a positive number down to a negative number. Okay, so you can see that there is one more graph that I have yet to highlight. And that is because I forgot to pull out a nice purple pen. There we go. I've got a nice purple pen. This is a purple graph. So let's look at this. This is our friend that came along with our green guy. So here's x cubed, and I forgot to mark that, so let me mark it right now. This is h of x equals x cubed. And so the question is, why did we get this purple one? What's going on there? And the answer is, well, you can see it as a couple different things. But remember, we're focused on the concept with our transformations is, did the change happen inside the function or outside of the function? Is it inside the parentheses or outside? This happened outside, so this is going to be a transformation of y values. We went from a positive y to a negative y. Now this transformation happened inside the parentheses. So what we're going to be looking at is, for example, we've got this point right here, which is the point 1, 1, and that corresponds over here to the point negative 1, 1. Because, remember that concept of x has to, the word just went right out of my head. Yep, it's gone. Okay, so x has to make up for the minus. So this minus in there says if we want x to be equal to 1, well, technically we have to let x be negative 1, because then it would be the opposite of negative 1, which would be 1. So we have to flip every x value to its opposite. Oops. I got a little excited about all the pluses going on. So in this case, every positive x value switches to a negative x value, and every negative x value is going to switch to a positive. And so the reflection here is going to be top to bottom. So if we drew this and then folded the paper in half there and lifted it up, this would be like the squished image of it, if you've ever done that in art class. And then for these two, when we change the value that's going inside, we take this graph, which is complicated, right? It goes across both sides. We fold it along the y-axis and end up with the purple one. So we end up with a reflection. And so this is actually pretty beautiful. It has a beautiful way of being described. Is if there's a minus on the outside, you reflect across or through or about or around the x-axis. So you reflect top to bottom. And if you change the sign inside, you reflect across or about. I've heard it both ways, and there are a couple other ways to say it too. The y-axis. So this one's going to look like that. Now, what's interesting about this one? Well, what's interesting about this one is if you put a minus inside, because it's cubed, you're going to end up with a minus outside. So if you actually look at this one, could you imagine that instead of reflecting it this way, we reflected it top to bottom? And the answer is yes, it works that way too. So there are some functions that if I were to draw the green one in, if I folded the paper at the x-axis, I would end up with the purple, right? If this were wet ink and I folded it in half and pressed it together and opened it up, we'd end up with this one. So it actually works as a reflection across either the x-axis or the y-axis. Now, with the absolute value, that one has to be seen as a reflection across or about the x-axis, right, to get from this graph to this graph. So different graphs are going to have different characteristics, which brings us to the last topic of the section, which is even and odd functions. If f of the opposite of x equals f of x, then the function is considered even. So in other words, if it doesn't matter whether you put in a negative or a positive, you get the same answer, then the function is even. So in other words, in even land, that tells me that if I've got a graph, that every point I have over here, I also have a point over there. And they match. So if I do this, I go like that. It's not a great drawing, but you kind of see. And if I have a point here, would be duplicated over there, that sort of thing. So everything that you see on the left, you see on the right. And the question is there symmetry here? And the answer is yes. It's going to match left to right. So it's symmetric about the y-axis, left to right. Now, if f of the opposite of x equals the opposite of f of x, so in other words, minuses pass right through, the function is odd. This one's a lot harder. So with an odd function, trying to imagine what it looks like is kind of wonky. If there's a point here at 1, 2, right, then -1 would go to -2. So if I change the sign of the x, I also change the sign of the y. That's what that means. If I have a point here that says, let's see, it's, oh, that wouldn't be a function. Let me move it over just slightly. Let me put it right. Let's put it right there. -2, 1. Then I would have a point over here that would be 2, -1. Do you see how they... So this one would be the point. If this point were 2, 1, then this point would be -2, 1. So in other words, if x changes sign, the y stays the same. This one says if x changes sign, then so does y. And so the question is, does this have a symmetry? And the answer is, yes, it does. X cubed is odd. Absolute value of x is even. If you just look at the absolute value of x, you can see the symmetry, left to right symmetry in the original function, not the fancy transformed function. But the question is, look at just the green, like x cubed. Is there a symmetry? And the answer is yes. But the symmetry is weird. Is it left to right? And the answer is no. Is it top to bottom? And the answer is no. The symmetry is, if you imagine we put a pin right there, and then we spin it around. We turn the whole thing around 180 degrees. So we spin it. This is symmetric about the origin. Now, in my experience, this one, the symmetry about the origin, is really weird. It's really different. And if you've never seen this before, this could take a little time. What I can do here, let me draw this graph. I'm going to copy this. So this is y equals x squared, x cubed. So I claim the symmetry is about around, across, through, under, over the origin. So what I'm saying is if I take and I hold that point and I spin it around, I end up with the same function. That's what symmetry about the origin is. It's a rotation, except rotation is something else. But to humans, it looks like a rotation. So it's kind of cool. So does that work with this guy? So if I put my finger there and I turn it around, no, you end up with the other one. You don't end up with the same one. So odd functions are special in that if you spin them like a pinwheel, you end up with the same function. Okay, so what do you think was the reason for the names odd and even? Odd, y equals x cubed. Yeah, it's odd powers of x. And even, oh, here comes Chai. No, Chai, we're almost done. Chai, sweetheart. I will play with you in just a second. Even something like y equals x squared is even. So it has to do with the exponents. The powers of x, odd powers are odd functions. They do that pinwheel thing. Even functions, even powers are even functions, which means they do the full D thing. Okay, this video was truly a lot. Definitely take your time, do the homework, ask lots of questions, ask for examples, and be gentle with yourself, because if this is the first time you've come across all these concepts, it's a lot to take in, but it's worthwhile, because the more you understand about the way functions work and the way functions are related to each other, and for example, you can take this graph and write it like this graph and so on and so forth. If you start to understand this, all the graphing you're going to do in the future is going to be a lot easier. I really recommend, if you can take the time and just go into Desmos and just try different things. Plug in, plug in these functions. Plug in all these functions and start playing. Put 2's in, put negatives in. See what the graphs look like. Watch to see how the graphs move around, and you'll get that innate sense of how to manipulate functions to get them to do what you want. So, but definitely now take a break. Go look at something green. Go look at something far away. Give your brain a break. Give your eyes a break. Maybe donate to the fund to help pet kitties who are feeling very ignored right now. Chai is the president and founding member, and get a snack and something to drink, and really appreciate yourself and your brain for doing such a great job and making it, getting through, sticking with it, and hopefully the homework goes really well. If not, ask me, and otherwise, woohoo and math on.